Okay, let's start class. I think last time we stopped here. This is the. So we talk about the likelihood ratio test, Pearson's chi-square test. We test the independence on the contingency tables. So compare these two tests, Pearson's and the likelihood ratio test. They both have the same limiting distribution. So when the sample size is large enough, they both converge to the chi-square distribution with I minus 1 times j minus 1 degrees of freedom. I is the number of rows, j is the number of columns. Okay. And for the small, so for large sample size, they're equivalent. But for the small sample size, they may perform differently. Why? Because they approximately follows the chi-square. So the quality of the approximation really depends on the sample size, right? So when we compared Pearson's and the likelihood ratio test, we found that the convergence of the test statistic from the Pearson's chi-square test is faster than the convergence rate for the likelihood ratio test. In other words, for small sample size problem, Pearson's chi-square test statistic follows more closer to the chi-square distribution. It has a better approximation. So therefore, the Pearson's chi-square test performs relatively better for small sample size compared to the likelihood ratio test. Okay, but when the sample size is large, they are equivalent. Okay, so you may ask, so how large is large? How small is small? Right? So here, this gives you some very simple rules. So when the average counts per cell is less than 5, then we say the likelihood ratio test statistic, the G square, is usually not follows a chi-square distribution well. Okay, so you have to be used very cautiously when the average count is less than 5. Okay, and for the Pearson's chi-square test, this is usually valid, even though the average count is no greater than 5. Okay, so just give you the idea that if the sample size is small, use the Pearson's chi-square instead. Okay, so the chi-square test, both likelihood ratio and the Pearson's chi-square test, only tests we reject the null hypothesis or fail to reject the null, right? It then tells you the direction that it go to if we reject the null hypothesis, right? Because the alternative is usually two-sided, right? Or much general. It doesn't tell you which direction it goes. Okay, so in order to see the direction, what we can do is after we conduct the test, then we can check the residuals. And to see the size of the residue, then that can tell us the deviation is to which direction. Okay, so let's see so let's see this party identification example again. Okay, so in in this table, those numbers not in the parentheses, these are the observed counts. And those numbers in the parentheses, these shows the standardized residuals. Okay, so why we need to use the standardized residuals, not just the raw residue. So the raw residue is defined by what we observed, Nij, right? Minus what we expected if they are independent, right? So this is the raw residue. Why not using this? Because we don't know the distribution of this. So we need to standardize it. So after we standardize it, we know that under the null hypothesis, this one follows approximately a standard normal distribution so that we can check if this is significant or not. So that's the purpose. So we need to standardize it. So instead, we use the standardized residue. And this is the standardized residue. So this is the numerator is the residue, right? Divided by the square root of this, which is, so the denominator is nothing but the standard error for the numerator. Okay, so just standardize it so that it follows a standard normal. Okay, and the rule is when the table size is small. So what does that mean? That means the number of rows times the number of columns is small. So we don't have much cells. It's not the counts per cell. It's how much cell we do have. Okay. So if we don't have lots of rows, we don't have lots of columns, then we can use the 2 as the threshold. So if the residual absolute value is greater than 2, then that shows some outlying residues. Okay. If it's within 2, then not outlying. Okay. And if the cell size or if the table size is large, that means we can have either some large number of rows or large number of columns or both. Then we should use 3 as the threshold. And you may ask why we need to worry about this, the number of rows times number of columns, because that's just like multiple comparisons. Okay, if we have too many groups, of course we need to have a more outlying threshold because we have so many groups, combinations, right? So we need to have a higher threshold. Okay, because even though none of them have some true deviation from the null, but just because the size, the number of groups becomes larger and larger, we may observe some false positive. That's very obvious, right? So that's why this is related to the table size. Okay, so if table size is small, we use 2. If table size is large, we use 3. Okay, and in our case, you can see the standard residue for the female democratic, that's 4.5. Obviously, that's beyond the threshold. Okay, and you can see for the males, that's this. For the Republican females, males. So this tells us what? So this tells us if the gender and the party identification are independent, if these two are independent, and we can easily see that there was an outlying. So the females in the Democratic is much higher than what we expected, right? And the females in the Republic is much lower than what we expect, right? Or we can say that females are more likely to identify themselves as Democratic, while the males are more likely to identify themselves as Republican, right? And from the residual analysis. So this tells us the direction of the deviations, okay? And we can also check the odds ratios to see that. So if we check the odds ratio between the two parties, among male and females, and you can see the odds ratio is 1.6. Okay, so that's the, and so that means what? The odds of identifying with Democrats rather than the Republican is 6%, 60% higher for the females than the males, right? So that's one way to identify, to interpret. Or we can interpret as the odds of being the odds of having the females rather than the males to identify themselves as the Democratic is 6%, 60% higher, right? So this is how we interpret the odds ratio, and you can choose the one that is more appropriate, right? So this is the residual analysis. And this one is talking about the partitioning the chi-squares. So here you can see when we do this, we only consider the Democratic, Republican, male, females. But in the table, we also have an independent party, right? So you can see that here in some case, we can have multiple rows, multiple columns, right? And sometimes we only focus on a subset of rows, a subset of columns, right? So what is that relationship with the whole table? Okay, so it tells us in some way, it's not always, in some way we can partitioning the chi-squares by choosing a subset of rows and columns, okay? So here is the, so for the chi-square distribution, okay, if these twos are independent, then we can say the sum of these twos follows a chi-square with degrees of freedom is df1 plus df2. So we can add these two. Okay, so let's say if x follows a chi-square with degrees of freedom is df1, right? And the y follows a chi-square with degrees of freedom is df2. Okay, and if x and y are independent, then what is the distribution for the x plus y? And it just tells us x plus y follows a what? Follows a chi-square with, we can add this degree of freedom. So that's the property for the chi-square, okay? So this, based on this tells us we can also partitioning the tables like that, okay? For example, the party identification example, we can partition the table into these two ways. So the first one is compare the Democratic with independent. Okay, so we have these counts, right? And then another way we can do is we combined Democratic and independents and against the Republican for the female males. Okay, so then for the table one, the one that on the left, okay, we have the chi-square test statistics using the likelihood ratio is 1.8. Likelihood ratio test is 1.8. And for the table two, the one that on the right, we have 28.2. And if we just apply the likelihood ratio test on the raw table, we have 3 parties and 2 genders. So the test study for the likelihood ratio test is 30.0, which is the sum of these two. So you can see we can partitioning the original 2x3 tables to these 2x2, 2x2 tables. And you can see the test statistic is add together is the test statistic for the original tables. So this tell us what? And you may ask why we need to do that partition. So this also tell us something. Since in this table, it's 1.8. So that means we don't have a strong evidence to see a difference between the male and female among the Democratic and Independent. Okay, but for the Republican against non-Republican parties, which include both the Democratic and the Independents, there is a very strong difference in the distributions between the male and female. In other words, male tends to identify themselves with Republicans, while the females tends to identify themselves as Democratic or Independent. Okay, so that's how we interpret it. Okay, but I have to say that it's not all types of petitioning that follows that. If you want to know the detail, read the textbook. It gives you some guidelines to how you petitioning the tables so that you can keep this relationship. Okay. Okay. So that now we talk about now. Previously, we always we only focus on the tables with x and y's are both categorical. Okay. Now let's see what if one of them is ordinal. Okay. So ordinal is different from the categorical, is different from the categorical variable because it has a order information in it, right? So if one of them is ordinal, okay, now here, so there are 2 possible ways to have one ordinal, right? If we have an x and a y, okay? So if x is ordinal, y is categorical. So that's one situation. And another situation is if x is categorical, y is ordinal, right? So we will consider both, okay? So first, let's see if x is ordinal. Okay, so x has some orders, but y is binary. Okay, so let's see. So here, this is the example. So here the x is the alcohol consumption. Okay, so we have 5 categories. Okay, so the first one is 0, means it's not so the subject does not drink alcohol. Okay, and less than 1, 1 to 2, 3 to 5, greater or equals to 6. So these are the number of drinks per day. Okay, so the first one is it's not a alcohol drink. Okay, and Y information tells the malformation for the firstborn baby, absent or present. Okay, so these are the observed counts in a study. Okay, and here, of course, the X, the alcohol consumption is an ordinal variable, right? We see the orders. Okay, and we want to check if there is a trend between the alcohol consumption and the proportion of the malformation infants. Okay, and particularly we are focusing on some linear trend. Okay, why? Because if we run the chi-square test, okay, just consider the alcohol consumption follows is a categorical variable, not ordinal. And we look at the standardized residuals, and we do see some increasing trend, right? So that means if there's no association between the alcohol consumption and malformations, okay, you can see the residuals is increasing when the alcohol consumption is increasing. So that means the expected occurrence for having the malformations infant, okay, is much lower than what we observed for those subjects that have high alcohol consumption. What we observed is much higher than what we expected for those high alcohol consumption group, right? So that tells us something, okay? So let's see if we can do the linear trend test. So since X is ordinal, so we need to assign some scores. Okay, so this part is the most difficult part because it's subjective. Okay, so in practice, if you want to test the linear trend and you want to assign the scores, you have to justify why you use that. Okay? And also maybe you can have different choice. So sometimes you may apply these different options to see if that makes a different conclusion or not. If they all gives you the same conclusion, that's fine. If it's different, then you have to see which one is more appropriate. Okay, so let's say, suppose now we have the row scores. Okay, so we have U1 through UIs. Okay, for the columns, we also need to assign the scores if it has more than 2 groups. But here it doesn't matter because here the column, the response is binary. So we don't have to have a ordinal Y. Even though just binary, it's not ordinal, but we can still assign 0 and 1, right? So that's a special case. Okay, so let's say the 0 is absent, 1 is present of malformation. Okay, but so this one is not a problem in our case. But for the row scores, how do we assign that? And here, in this case, what we can do is we can assign the midpoint for the range, midpoint of the range. Like here for the 0 one, of course we can assign as a 0. That's a very natural score for the group 0, right? For this one, we can use 0.5. How about that? Because this is between 0 and 1. Let's just use the midpoint, right? What about this one? This one between 1 and 2, let's just use 1.2 or 1.5. Midpoint of the range. For this one, use 4, right? For this one, this is kind of arbitrary. We can use 6. But here, because this is greater or equal to 6, so using 7 seems to be also a reasonable, right? So anyway, this is just the one possible way to do the score. And you can try others, okay? But that's seems to be reasonable, right? So these are the scores we can assign to the alcohol consumption. Okay, so after we assign the scores, then and for the alcohols, we can assign 0 as absent, 1 as present. And you may say, why it's 0 for absent? Why not 1? That's fine. If you switch it, it doesn't matter. The result is the same. Okay? Or if it's 0, 1, why not 0, 2? That's also fine. It don't want, if it's binary, it won't change the results if you treat as 0, 1 or 0, 2. Okay? But if it's more than 2, then it will make a difference. But here it doesn't. Okay? Okay, so then we have the, after we assign this, then we can get the sample average of the row scores and sample average for the column scores. And that's very obvious. It's the weighted sum, right? So the weighting is the proportion. It's the row proportions and the column proportions. Okay, so it's just then after we find out the sample average for the row scores, sample average for the column scores, then we can use this formula to find out the sample covariance. Okay, so the sample covariance is this one. Is the numerator. You can see it's the summation for all the cell rows and columns for the mu I minus mu bar times Vj minus V bar. So the U bar is the sample average for the row sum. Okay, V bar is the sample average for the column scores. Okay, and the Pij, that's the proportion of samples for the ith row jth column cell. Okay, and divide by the square root of these. Okay, so after we get the R, then if the so the null hypothesis, let's say independence, against alternative says rho is not equals to 0. So that means if we have some linear trend. Okay, rho is the correlation. So the test statistic is what? Is the m square. So what is m square? M square is m minus 1 times r square. R is this one. So we have the square of the r times m minus 1. What is n? N is the total sample size. N is the total sample size. Okay, so in this study, what is the total sample size? The total sample size is just you add all these numbers together. Okay, and you will have the total sample size is 32,574. That's the total sample size. Okay, so n is the total sample size, and the m minus 1 times r square. And that is the test study for testing the linear trend. Okay, so if the null hypothesis is true, that if they're independent, that means row variable, column variable, these are independent. There's no linear trend. Then the m square follows approximately a chi-square distribution with degree of freedom is 1. So that's under the null. Okay, so if it's a very large number, then this indicates we have a linear trend. Okay, so we will reject the null hypothesis if we have large values for the m square. Okay, and also we can do it as a one-sided test. So if the alternative says not rho equals to 0, because that's two-sided. So rho is the correlation not equals to 0. It includes two possible cases, right? Rho is greater than 0. That means it's a positive association. So the linear trend is positive. It's like that. Okay, or it also includes rho is less than 0. So that's a negative linear trend, right? So if the alternative is one-sided, let's say we are pretty sure it's positive linear trend or independence, right? So then it's one-sided, then we can use the m as the test statistic because the chi-square only tests two-sided. So we can use m instead of m squared. So m is r times square root of n minus. So that will follow the normal distribution with 0, 1. Okay, standard normal. So that's how we test it. So in this case, if we just consider the alcohol consumption as the categorical variable, totally ignore the order information. Then you can see for the Pearson's chi-square, we got the test statistic is 12.1. The p-value is 0.02 with degree of freedom is 4. Why? Because how many rows do we have? So here I equals to what? 5, right? And j equals to what? How many columns? J equals to 2. So what is the degree of freedom for the chi-square? It's I minus 1, right? Times j minus 1. So I is 5, that's 4. J is 2, that's 1. So that's why this is 4, right? So you can see for the Pearson's chi, it's significant. That means there is a significant association between the alcohol consumption and the malformation of infant. But if we use likelihood ratio test, you can see it's actually not significant. The test statistic is 6.2, the p-value is 0.19. So you can see there is a big discrepancy between the chi-square and Pearson's chi-square and the likelihood ratio. So that's a warning sign. Remember last time I tell you if the chi-square for the Pearson test and the chi-square for the likelihood ratio test give us different results, it's a warning sign said that means the chi-square approximation is not good. And that's obvious because you can see in this study, it's highly imbalanced, right? So we have lots of counts for the absent with low alcohol consumption group, but we just have very little counts for those with malformation and a high alcohol consumption group. So you can see highly imbalanced. So that's why the approximation for the chi-square distribution is no good. And that also gives you some idea that likelihood ratio test doesn't give you as good as the chi-square for the Pearsons. You see that? The likelihood ratio doesn't detect the trend information. But Pearson's chi-square does find some. Okay, but the Pearson's chi-square is very general because the alternative only says they are associated. What kind of association it is, you cannot tell from the Pearson's chi-square, right? Because it only rejected. And you can see from the residues, there was some increasing trend. Okay, but to rigorously testing it, we can use the test that we mentioned here. Okay, so we can test the linear trend. And to test the linear trend, we have the m square is this one. This is the total sample size minus 1 times this is the r. Okay, and you can see the test statistic is 6.57. And this follows a chi-square with degree of freedom is 1. Okay, so the p-value is very small, is 0.01 for the two-sided and 0.005 for the one-sided. So either one suggests a very strong evidence of non-zero correlations, and that correlation is obviously positive. Okay, but here you can see the correlation itself is 0.0142, seems to be a very small value. Okay, it seems to be weak but highly significant because of the large sample size. Here the sample size is 32,000. Okay, so and because of the imbalance, it's so small, but it's still significant because of the large sample size. So you may ask why we need to use this test. Why not just use the Pearson's chi-square? What kind of gains we can have? What is the benefit of using this test? Okay, so here in the hypothesis test, you need to keep in mind that if the alternative hypothesis is very general, then the power is always very low compared to the alternative is very specific. Okay, so like the ratio test or Pearson's chi-square test for independence. What is alternative? Alternative says is they are not independent, but there are many, many types of association we can have instead of independence. So you can see the alternative is very general. So there are many possible directions is included in the alternative hypothesis. So that's why for such a general alternative, the power of the test is very low. And that makes sense because there are so many possibilities in the alternative that it includes. So to identify that, the power is low. That means the probability of, so the chance of rejecting the null hypothesis, if the null hypothesis is not true, is relatively low. Okay? And if we know that the direction of the alternative that will be, so the direction of the deviation that will be from the null hypothesis, then instead we can specify a more specific alternative, such as we know that if the null hypothesis is not the case, if they are not independent, then it has to be some linear trend. And you are sure about that. Then we can specify the alternative in a much specific way, in a much specific direction, says this follows a linear trend as a alternative. Then in that case, the power of the test will be much strong, much higher. That means the chance of rejecting the null hypothesis is much larger if we have a more specific alternative. But you also need to aware that there's no free lunch to get from these tests. Why? Because having a more specific alternative also has a very potential risk of, if you don't have that information, if you misspecify your alternative. In other words, if the alternative is not actually follows, if the truth does not happen in the direction that you specified in your alternative, then the test that you are conducting cannot identify, cannot catch that deviation from the null, because you are specifying the alternative in a wrong way. Okay, a very obvious example is one-sided alternative or two-sided alternative. That's always a very interesting question for so many statistics practitioners. Should we specify a one-sided alternative or should we specify the two-sided alternative, right? So if we specify the one-sided, the power will be higher. We are easier to reject the null. If we specify the two-sided, it's more difficult to reject the null hypothesis, right? And everyone wants to reject the null hypothesis. But should we really go with one-sided alternative? It's not the case. Because if you misspecify it as a one-sided, and if the truth goes the opposite direction, then you cannot detect the difference. So that's the potential risk that you are taking. That's one thing. And the second is, sometimes if you see the data and then specify the alternative, then that is cheating. That will cause a bias. And if the reviewer know that you choose the direction after you see the data, that result cannot be published because that will increase lots of bias. Okay, so there are many issues. So in practice, if you are not sure that is the direction, if the null hypothesis will go, then you should not specify, you should not use a specific alternative. You should use a more general. Okay, so these are the things you need to know for the test, hypothesis test. Okay, so in this example, if you want to do it in the R, this test, the M-squared test, is available in the R in the CMH test, okay, which is called Cochrane Mental Hansel test statistic. Okay, so I have the code here. So this function is in the VCD extra library in the R. Okay, you run the test, the one that I highlighted. That's the and that gives you the chi-square, gives you the m square values with degree of freedom is 1. That's the p-value. Okay, but this p-value is two-sided. If it's one-sided, you need to divide by half, divide by 2. Okay, and this one is general association. So this one is just based on the Pearson's chi-square without any specific alternative saying this is a linear trend or not. No. So this is 12.08. That's the Pearson's chi-square test. Okay, and the p-value is 0.02. That's the Pearson's chi-square. Okay, and this one tells why we need to use the m-squared test here, because this can give us extra power with the ordinal test. Okay, so where does the extra power come from? Because the alternative is more specific. That's one reason. Another reason is it utilizes the order information from the row and column variables. That's the second reason. And the third reason is that the statistics for the m-squared test is follows a chi-square with 1 degree of freedom. So degree of freedom is 1. That means the smaller the degree of freedom, the more significant the p-value is. Is that right? So if you look at the tables, where is it? If you look at the chi-square tables, okay, and let's say for the 0.05, look at the threshold at 0.05. If its degree of freedom is 1, the threshold is 3.84. That means if you have 3.84 or larger, you will have a significant result. But if we have more degree of freedom, the threshold becomes higher and higher. That means we have more and more difficult. It's more and more unlikely to reject the null hypothesis, right? Because the threshold goes higher and higher for large degrees of freedom. Okay, so that's another reason. That's why the power is higher for the m-squared test. Okay. So the choice for the score matters. So here, if I change the score to 1, 2, 3, 4, 5, okay, so previously I choose the 0, 0 0.05, 1.5, 4, 4, 7.0, right? This is the score that I chose for for these 5 categories. But here, instead, we choose 1, 2, 3, 4, 5. Okay? If we choose that, you can see the test results will be very different. Okay? So the test results is 1.83 for the m squared, and the p-value is not significant at all. Okay? And also, the relative spacing is what is important. If we choose these 1, 2, 3, 4, 5, it will be the same as 0, 1, 2, 3, 4. That means if we shift it a little bit, if we multiply it by a constant, it's the same. So using 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, or 2, 4, 6, 8, 10, these are all give you the same 1.83 because the relative spacing is the key. Okay, shifting by a constant or multiplied by a constant, it doesn't change the test study. Okay, so another way is an automatic way to assign the score by using the mid-rank. Okay, and if we use the mid-rank, you can see the p-value is even larger. The test study is even smaller. Why? Because the table is highly imbalanced. If we use the mid-rank, it's really these groups matters. These groups are ignored. Why? Because they have so few counts. So that's why using the mid-rank or 1, 2, 3, 4, 5 gives too much emphasis on those large cell counts. But while ignoring those high alcohol consumption and presence malformation group, which makes the test not significant. Okay, so play with this. Okay, find these numbers after class and think about it, and you can easily understand. So to choose an appropriate score is really important here. Okay, if you don't choose it wisely, you probably cannot identify the treatment effect. You probably cannot identify the linear trend effect because, especially for this case, which is imbalanced. Okay. Okay, so in this example, we have 2 columns, but 5 rows, right? What if we have the opposite? What if we have 2 rows, but j columns? In other words, now this time, what if the y, the response is ordinal, but the x is binary? Okay, for example, if the response, so here, this is response y, okay? Y has 3 categories. It's ordinal because it's really showing the diabetes status. The first one, the group 1 is no diabetes. The second is pre-diabetes, and the third one is diabetic. So we can put them in the order, right? So let's say this is rank 1, rank 2, rank 3, right? In that order. Okay, but the X is binary, male and female. Okay, so can we do the test for this case? So Y is ordinal, X is binary. Okay, yes, we can do that. We can do it using a test called the Wilcoxon-Ransom test, also called the Mann-Whitney test. So Mann-Whitney test and the Wilcoxon-Ransom test, they are 2 different tests. Test statistic is different, but they're equivalent. Okay, and you may ask why the test statistic is different but equivalent. It's just like the chi-square test with degree of freedom is 1 and the standard normal test. They can be equivalent, right? But the test statistic is different because we have to take a square to make it that. Okay, so there's a relationship between these, and conclusions are the same. So it's possible, okay? So Mann-Whitney and the Wilcoxon-Ransom always give you the same conclusion, but the test statistic is different. This is based on the Ransom, okay? But Mann-Whitney is different. So here, in this case, we use the Wilcoxon-Ransom test, which is a non-parametric version of two-sample t-test, okay? And we can, so Wilcoxon-Ransom test, based on the name, you can see it's based on the rank, okay? And the test statistic is the sum of the rank for the observation in one of the group, okay? So two rows. The test statistic for the Wilcoxon-Ransom test is just the rank sum for one of the rows. Let's say the first row, okay? And you say, what about using the sum for the second row? It's the same. The test results, the p-values will be the same, okay? So it doesn't matter. So here you can see the test statistic is 1,578. That's, I think, it's the sum, the rank sum for the first group, okay? And the p-value is 0.01397, which is significant. So that means so the null hypothesis says there's no difference of the diabetes status distribution between the male and female. And the test result says there is some difference between the male and female in terms of the diabetes status. Okay? And you may ask then, what is the difference? Okay, what is the direction of the difference? And you can see that from here, just by looking at the counts, you can see the females tends to have no diabetes, while the males tends to have more diabetic or pre-diabetes symptoms compared to the females. Is that right? So that's the difference that happened between the male and females. Okay, so okay, so any other measures for the ordinal data? So here, this is we do have some other measures like the Spearman's rank correlation. This is the non-parametric version for the Pearson's correlation. Why? Because this is based on the rank instead. Okay, so if the Spearman's rank correlation is close to 1 or -1, then that means the higher rank value of y are associated with the higher, if it's 1, or lower, if it's -1, ranked value of y. Okay, and if we have a tie, we use mid-rank. Okay, so what does mid-rank mean? Mid-rank, let's say, if we have 3 1s, 3 2s, 3 3s, okay, and put them in the rank. So of course, these threes will have, so we have 9 observations, right? So we should have rank 1 through rank 9. But since the first threes are a tie, so what we can do is, instead of assigning them 1 1 1, we can just use the mid rank 2 2 2 as these 3 observations rank. Okay, then the next is, we have the next 3s are the 2s. So that's the second rank. So they should have, since we used 1, 2, 3, so we have rank 4, 5, and 6, right? So we use the mid rank because we have a tie. So we use 5, 5, 5. So these are the mid rank for these 3 observations, right? Then we have 7, 8, 9. So since we have a tie, so we use 8, 8, 8. So that's the mid rank. Okay, so that's how we deal with the ties in the mid rank. And another one is the Goodman's Kruskal gamma. So this measures the association this one is just the Pearson's rank. This is just the Spearman's rank correlation is just the Pearson's correlation, but replacing the X and the Y by the rank of the X and Y. Okay, so that's the only difference. For the Goodman-Kruskal gamma, this measures the association between two quantitative or ordinal variables through the concordant pair, discordant pairs, and then use this formula. So what is the concordance pair? That means we have n subjects, okay? And how many pairs we can have? We have n choose 2 pairs, right? So let's say we have 10 subjects. So how many pairs we can have? We can have 10 choose 2, that's 45 pairs, right? 45 pairs. Okay, for each pair, if the rank higher for each pair, if the subject ranks higher on X, also have the rank higher on Y, then we say this is a concordant pair. Okay, so for these 45 pairs, let's say one of the pair, we have 2 subjects, A and B, right? If A has higher rank on X and also has higher rank on Y compared to B, then this is a concordant pair. But if X but if A has higher rank on X but lower rank on Y, then this is a discordant pair. Okay, so now we have NC, that's the concordance pair, the number of concordance pair. ND, that's the number of discordant pair. So NC minus ND divided by NC plus ND. That's the gamma coefficient. Okay, so if the gamma is close to 0, that means they're independent. If it's close to 1, positively associated. -1, negatively associated. And by the way, for these 2 measures, we have to have a paired data structure. Okay, so what does paired data structure mean? Paired data structure means that we need to have each observation has 2 measures, measure A or measure X and Y for each pair. So we have the subject 1, subject 2 to the subject N. Okay, and we have 2 measurements, X and Y, for each subject. So that's called a paired structure. So each subject has 2 measurements. Okay, if we have that structure, then we can use the Spearman's rank and the Kruskal gamma. If we don't have that such pair structure, we cannot use these 2. Okay, but compare with these, we don't have pair structure here. We don't have pair structure here, right? And we don't have paired structure also here. So you have to be very careful, okay? So different measures are really fit for different types of data. Any questions so far? Okay, now this is the Fisher's exact test. So this is for the 2x2 tables and for the small sample size. Okay, and for large sample size, we don't need to worry because we can always use the Pearson's chi-square or the Spearman's and the likelihood ratio test, right? So, but if we have a small sample size, then both these tests didn't work well. Okay, so here we can instead use the Fisher's exact test, which is exact. There's no approximation here. Unlike the likelihood ratio test and Pearman and the Pearson's chi-square test, they are both approximation is used, okay, to approximate the chi-square. But here we don't have large sample approximation for the Fisher's exact. It's entirely exact. Okay, so here for the Fisher's exact test, if we have 2 by 2 table like that, okay, with the margins are fixed. So what does that mean? That means those row sums and the column sums, these are fixed. Okay, then we can tell that one of the cells determines the rest. Okay, is that clear? So if, let's say, n, the row sums and the column sums, these 4 numbers are fixed. Okay, then if we determine the n11, then the rest of the 3 cells are determined. Why? Because you can see here, this table is showing UY. So if n plus 1, n plus 2, and n1 plus, n2 plus, these are the row margins and the column margins are fixed, then if we only know n11, the rest of the 3 cells can be expressed by the row sum, column sum, and n11. Why? Because if this is n11, this one becomes what? This one becomes n1 plus minus n11. Is that right? And what about this one? This one becomes the first column sum, n plus 1 minus n11. Is that right? And what about this one? That's just the total sum, n minus the row sum for the first row sum, first column sum plus the n11. You see that? If the row sum, column sum are determined, as long as one of the cells is determined, the rest of the 3 cells are determined. And that's obvious. Why? Because what is the degrees of freedom? We have 2 by 2. So the degree of freedom is really 2 minus 1 times 2 minus 1, right? I is 2, J is 2. So the degree of freedom is actually 1. That means one cell determined, the rest of the 3 cells determined. Okay? So for the Fisher's exact test, we just use a distribution called hypergeometric distribution, which is this one, to calculate the probability of getting the n11 is this one. Okay, so before we look at the details, let's see the next slide. What is hypergeometric? Hypergeometric distribution describes the probability of having case success in n jaws without replacement from a finite population of size n that contains exactly capital K successor. So easiest way to think about the hypergeometric is, suppose we have a population. Okay, in this population we have n observations. Okay, but among these n's, k of them are success, and n minus k of them are failure. If you don't like to think about success or failure, you can think about, we have a large jar. That's the population. We have red ball and blue balls. We have k red balls. We have n minus k blue balls. In total, we have n balls. That's fine. Okay. So then we take out some of them. How many balls do we draw from here? We draw n balls without replacement. That means if we draw one ball out, we don't put them back to draw the next. No, we just take them out without putting back. Okay, so without replacement. We draw n balls. Okay, and here the hypergeometric distribution gives us the probability of having little k red balls or little k success out of this n. So what is the chance of getting that number of success or that number of red balls from the n jaws without replacement? Okay, so the probability is based on that distribution is called hypergeometric. It is this one. Okay, let's see what is the numerator? The numerator is if we have K red balls or K success, right? From here. So the numerator tells us how many ways of having K success out of the capital K, right? Because capital K is the total number of success or total number of red balls. So that's describing the number of ways we can draw K success out of capital K. And what is the other one? The other one is very obvious. How many ways we draw N minus failures or N minus K blue balls out of capital N minus capital K. That's the total number of blue balls or failures, right? So that's the total number of ways we can get K success and N minus K failure from the population. But divide by what? Divide by the capital N over N. So this is the disregarding the K success and N minus K failures. How many ways we can have from N choose small n without the proportion of red or blue, without the proportion of success or failure. So this is the total number of ways we can get N different balls from the capital N. So the ratio is the probability of getting that. Okay, so that's the hypergeometric. So if you understand that, then you can easily find out this is a hypergeometric. Why? Because you can think about this is the population size, capital N. Now this small n becomes the capital N, right? And how many red balls? Let's just say we have this many red balls. Okay, so the first row means success or the red balls. And the second row means the blue balls or the failures. Okay, so we have N11 success. Okay, so that means N M1 plus over N11. That means that's the number of ways we can get N11 success out of the N1 plus. That's the total number of success or red balls, right? And this is the total number of failures from the population. And this is the number of failures we choose from the samples. Over, this is the population size. This is the sample size we got. Okay, so that's the Fisher's exact. So this gives the probability of getting M11 given the row margin and column margins are fixed, okay, from the hypergeometric distribution. Now let's see an example. So this is a very old data set from R.A. Fisher and a colleague of R.A. Fisher who developed ANOVA's F-test. So he's called the father of modern statistics. So his colleague says he could distinguish if the milk or tea was poured first in a cup of tea with milk. Okay, so then they conducted a test, an experiment. It has 4 cups with pouring the milk first, tea second. 4 cups with pouring the tea first and milk second. And then let his colleague try it. And the colleague find out 3 out of 4 with milk first, tea second. And 3 with tea second, tea first, milk second. And there are 2 mistakes. Okay, so we want to test if this colleague really have a significant way to identify which one pours first from this data. Okay, so this is a Fisher's exact. Why? Because we have a small sample size. And also the rows and columns are fixed. Why? We predetermined 4 cups with milk first, 4 cups with tea first, right? So these are fixed. So the null hypothesis says the theta is 1. That means theta is the odds ratio. Okay, if the population odds ratio is 1. So what does that mean? Remember, if odds ratio is 1, that means his colleague has no information about which one pulls first, right? So they're independent. The theta is greater than 1, that means his colleague has some information, okay? So the estimate of the odds ratio is what? Is the diagonal product divided by the off diagonal. So that's the 3 times 3 divided by 1 times 1. That's 9. Okay, if this is significant or not, we can do the test using the Fisher's exact test. So what is the p-value? P-value is the definition for, so this is one-sided. So is the definition for the p-value is the probability of observing what? What we observed or more extreme from the data, right? So what we observed is, let's just look at the N11. What is what we observed? That's 3 out of 4, right? So that's what we observed. And what is more extreme? In the more extreme case means we have 4 out of 4. Is that right? So the probability of getting N11 is 3 plus the probability of getting N11 is 4. That's the p-value for this one-sided test. Okay, so what is the chance of getting N11 is 3 using the hypergeometric? We have 4 choose 3, right? Times 4 choose 1. Divide by 8 choose 4. So that's the probability of getting N11 is 3. O plus the 4 choose 4 times 4 choose 0 over 8 choose 4. Right? So that is this one, it's equals to that. So the p-value is not significant. So that means, although it seems like his colleague has some information, but it's not significant. Why? Because we have a really small sample size. The only case we can make it significant is if the N11 is 4 and this one is 0. If that is the case, the p-value will be significant because this one is gone. Then we will have this. And only that lady can give the perfect answer that can make this significant. Otherwise, we cannot. If it's two-sided, then the p-value will be 0, 1, p0 plus p1 plus p3 plus p4. Think about it. Why? Because of the definition. So based on the definition for the p-value, you can see for the two-sided alternative, the p-value is p0 plus p1 plus p3 plus p4. Okay. So this is not significant. Okay. So the Fisher's exact test is very conservative because of the actual error rate 0.028 is smaller than that intended to be. So to diminish this conservativeness, we can also use the mid p-value approach for the Fisher's exact test. That is the half, using the half of the observed plus the probability of more extremes. So if we have the alternative is one-sided, N11 is 3, then the one-sided, then the mid p-value approach gives the 0.129. Still not significant, but it's different from the 0.243. Okay. And the Fisher's exact test can also be applied to the table size greater than 2 by 2. We can use the multivariate version of the hypergeometric distribution. But usually the Fisher exact is reserved for 2 by 2. Okay. Okay, any questions? Okay, the last topic for this one is the three-way contingency tables. So in some research, we have control variables that can affect both x and y. To study the effect of x on y, we need to hold the z as a constant. Okay? Otherwise, the effect of x on y may be the effects of z on both x and y. Okay? So that is very important. For example, if we have a cross-sectional study for the passive smoking effect, okay, let's say the Y is lung cancer or non-lung cancer. X is spouse is a smoker or non-smoker, right? But the secondhand smoking effect is confounded with the age and race. Okay, like the spouse of non-smoker tends to be younger than the spouse of the smoker, or a lower proportion of lung cancer cases among the non-smoker spouse just might reflect the younger age. So these results, the smoking effect, can be confounded with age and race. So in order to have a good understanding of these effects, we need to control the age group or the race group. Okay, so that's why we have a name called a partial table. That's a two-way table of x and y at each level of z. That shows the conditional association. It's like shows the relationship between x and y conditioned on a level on the z. Okay, and the marginal table, that's combining all the partial tables together into a table with only x and y, ignoring the z. Okay, so here the idea is if we don't control for the z, while if z can affect both x and y, then the analysis results can be very risky, can be even misleading. For example, let's see the death penalty here. Okay, so if we just look at the defendant's race and the death penalty from a study that is in Florida 1976 to 1987. Okay, if we just look at the defendant's race and the death penalties, okay, and we combine these together without looking at the victim's race. So if we combine these, then the marginal table will be what? Will be this one. This is the marginal table. Okay, look at the marginal table. Ignoring the victim's race. Look at this table. What is the percentage of death penalty rate for the white people, for the white defendant? It's 11%. For the black defendant, it's 7.9. So which race has a higher death penalty? White. Is that right? So that's obvious if we look at the marginal tables. But if we look at, now we condition on the victim's race. Let's say for the victims are white. Then look at the tables. You can see the percentage of getting the death penalty for the white defendant is 11.3%, while the black is 22.9%. So which one is having a higher death penalty rate? Black defendant. For the victim race is black, and you can see we have the similar conclusion. The black defendant has a higher death penalty rate, 2.8 against 0 for the white. So you can see if we control the victim's race, you can see the black defendant tends to have higher death rate. But if we ignore the victim's race, you can see we have the opposite conclusion. You see that? So that is called the Simpson's paradox. Okay, so we are running out of time. So read the last 5 slides. And next time I will go over that very quickly. We are behind the schedule. And one thing before we dismiss, I want to mention is look at the weekly schedule. We have a midterm exam coming. Okay, chapter 1 through chapter 3. So you can start to prepare for the chapter 1 and chapter 2. Okay, and next week I will give you some old exams for the exam 1. Okay, and we will discuss more details. The exam will all in person. So we will have the exams in some room in the Wooling halls. I will let you know the place. Okay, so start to prepare the exams and also work on the homework, work on the practice problems after each chapter. Seems to be should be a very good preparation for the exams. Okay. Okay. So let's stop here. Any
Doctor?
questions? Yeah.
So, Doctor, do you have the exam on February 17, right?